All right, here we go. 11.4. Here's the calendar. We actually have 4 weeks left of school, so you're looking at 3 of those weeks, and then that final week, the one that would be below there at the end there, that would be the semester final week. I'll give you that Monday, Tuesday, Wednesday as a review, and I'll just need you to complete the final on Thursday. And once again, this will all be I will be emailing you that final. All right. If that didn't make sense, send me your questions. I'll answer to them. Your homework's looking good. I'm getting it. Once again, if you have any specific questions, put it on your homework or send it to me in the email. Hey, show me how to do this one. I didn't get it type thing. All right. Homework for 11.4. And here we go. All right, if there is one section of the chapter that is algebraically or stepwise the most challenging one, it would be this one right here. All right, it's really only one thing, but it takes a while to get to it. It's a little bit more challenging. Luckily, this is going to be a video, so you'll be able to pause, rewind, play it a couple times. I'll just say this, if you pay attention and you do a couple of examples, it will make sense. I'm certainly not going to claim that this is the easy section, but trust me, it will make sense. All right, just one thing today. The formula is ridiculously easy. Unfortunately, there's some complexity hidden inside the formula that's only becomes apparent to you when you actually do some. All right, so super challenging to use it. How about that? So think about this. Way back when, chapter 3, we first started talking about polygons. The triangle is the first one. And we said that a polygon is closed. You can't get to the inside without crossing a segment. It's a plane figure, meaning it's on a flat surface. And it's made up of segments that are joined at their endpoints, triangle being an example. So that's it's closed. I can't get to the inside. It's flat, and it's made up of segments, and the segments must be joined at their endpoints. Today, we're going to be specifically talking about regular polygons. Now, we've talked about these before, but a regular polygon is a polygon where the sides have the same measurement and the angles have the same measurement. For instance, a square is an example of a regular polygon. All the sides have the same measurement and all the angles are 90. Now, what I don't want you to confuse is we're not saying the sides equal the angles or vice versa. We're saying that all the sides have the same measurement and all the angles have the same measurement. So there's a equilateral triangle, and that's a good example also in a square of a regular polygon. So 3 sides where the sides have all the same measurements and all the angles have the same measurements. So today is about calculating the area of regular polygons. And the way we get to the formula I'm about to show you is the fact that we can take any regular polygon and we can circumscribe, in other words, draw around it, a circle where that circle touches all the vertices of that regular shape, triangle, square, a regular pentagon, so forth and so on, regular hexagon, regular septagon, regular octagon. All right, they can all be inscribed. In other words, the circles circumscribe the regular polygon. Irregular polygons, there's a few that you can, but most irregular polygons, like this pentagon right here, it's irregular. The angles are different sizes. Notice not all the vertices touch the circle itself. There are a couple that can, a couple of exceptions. A rectangle is not a regular, sides are not all the same, and it can be circumscribed or it can be inscribed inside of a circle. All triangles can be circumscribed. And remember, when we did the construction chapter, that was one of the things that was on the test. All right. Key takeaway number 1 is that if you are regular, you can be either inscribed inside of a circle or a circle can be drawn outside and touch all the vertices of those regular polygons. Okay. Before we get to the formula for area, we're going to need a couple vocabulary words. Okay. So first off, that's the basic idea. I'm going to find the center of the circle, and it turns out that it's also the center of the polygon itself. So we will call that the center. Since it's a regular polygon, it's called the center of a regular polygon. It's also the center of the circle that circumscribes the polygon. Well, those are a lot of words. The picture's worth 1,000 words. There's the picture. It's pretty self-evident there that circle, or the center, is the center of both shapes. All right, if I draw a line from the center of either the circle or the polygon, to one of the vertices of the regular polygon, we're going to give that a name. If you notice, if you look at that and erase the polygon, well, that's a radius. So there's our next one, and it's called the radius. Not only is the radius of the circle, it's also the radius of the regular polygon itself. And so we're going to call that the radius of the regular polygon as the distance from the center of the polygon to any one of the vertices of that regular polygon. And by the way, it's also the radius of the circle. Okay, one more vocabulary word. Same shape, same idea as center, but this time we're not going to go to one of the vertices. I'm going to go to the midpoint of any one of the sides. So there's the radius right there. You could draw a second one, and hey, look, I made a triangle, right? And that angle that I'm pointing to right there, right? I'm sorry, or the angle right there. Notice, erase the polygon, and you got a central angle. So that's called the central angle of the regular polygon. A little bit hard to do, but just imagine that the pentagon was not there. You'd have your normal central angle. So the definition says the angle formed by two radii drawn to two consecutive vertices of the regular polygon. All right, makes sense. So far, so good. And then the last one, I kind of lied. I said that this was the last one. The last one, this is the new word, right? I'm going to drop a line or a segment straight down from the center of the circle or the regular polygon to the midpoint of any one of those sides. And this is the new one. It gets a weird name to it, but it's pretty simple. It's called the apothem, A-P-O-T-H-E-M. So it's called the apothem of the regular polygon. And it's that distance from the center of the regular polygon to the midpoint of any one of its sides. And notice, remember, we always measured distance perpendicularly. It's a perpendicular distance as well, too. All right, so 4 basic vocabulary words. All right, quick note, radius and apothem are mixed up all the time. So I mean, this is a little slightly confusing, this picture right here, but look at the blue. The blue goes from the center of the hexagon to a vertice, vertex B or vertex D, and that's why it's called radius. The red goes to the middle of one of the sides of that hexagon, therefore it's called the apothem. And lastly, what's lost on this is you have a central angle. So for instance, angle BAD or DAB, that is the central angle of the regular polygon. So there's all the vocabulary words thrown together. What you can't confuse, though, and I should say you can confuse them very easily, but what you should not confuse is the apothem and the radius. Usually when you get this wrong, it's because you're thinking apothem and you calculate the radius instead. All right, so that's the apothem, and that's the radius. Apothem, radius, apothem, radius. Okay, second note. Hey, remember, we can circumscribe this regular polygon right here with a circle. And if we go completely around the circle, we've gone 360 degrees. So if we go 360 degrees, that's from that red dot all the way around, then the central angle can be calculated as a portion of that 360 degrees. In fact, the way this is drawn right here, since all of those are going to be regular triangles, then you simply count up how many triangles you have there and divide 360 by that number. Since there's 6, are they purple, I believe? 6 purple triangles, then each one of those central angles would be 60 degrees. 360 divided by 6 purple triangles is 60 degrees. Lastly, see where the apothem is? The apothem would cut that 60 degrees in half. In other words, that angle would be 30 degrees. Let me pull out my pen here real quick if I can. Work with me, work with me. It's not, oh, there it goes. Annotate. Let's make it blue. Yeah, blue's fine. So I'm talking about this angle right here, right there, scribble, 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 is 30 degrees. Why? Because this angle right here is 60 degrees. Where did I get that from? Well, there's 6 purple triangles. There's 360 degrees in a circle. 360 divided by 6 is 60, and then half of 60 is 30. We will use that fact here quite frequently today in today's lesson. Okay, so 360. Let's see, what else do I want to know? Third note. we got to give names to these things. So abbreviations. So we're going to use the obvious ones. Let's see, we'll call radius. What do you think? How about we call radius R? We'll call the side length S, we'll call the apothem A, and the radius R. I did that backwards, but you get the idea. So radius is going to be R, apothem is going to be A, and side length is going to be S. And remember, side length is all the sides have the same length. All the radii are equal. All the apothem, because it's regular, will all have the same measurement. All right, how is this going to get us to an area of a regular polygon? That's what's next. So I'll do the proof of it real quick, and it's a pretty easy proof for a change. All right, let's see how it works. So I'm gonna call this a talking proof. I don't formally do like a T-table or a T-diagram where we have statements on one side, evidence on the other side, start with a given. I'm just gonna talk my way through the proof. All right, so think about this. If I take any regular polygon, there's a regular octagon right there, and I consider one of those triangles formed by the central angle. So there's the central angle. Remember, central angle is connect two adjacent vertices of the regular polygon to the center, and you make a triangle. Okay, so consider one of those triangles right there. I'm going to label the side, and it's apothem, so I need side S, apothem A. Okay, and I calculate the area of that triangle. Well, area of triangle is 1/2 base times height, or base times height divided by 2. Hey, look, apothem is also the height of that triangle. So that would be SA divided by 2, or 1/2 SA. You with me? All right, so consider that entire polygon now. That entire polygon is made up of triangles that have the same dimensions. In other words, they have the same A, they have the same S. So let's count triangles. 1, 2, 3, 4, 5, 6, 7. Total of 8 there, right? So there's a total of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. I confused myself there for a second. It's an octagon, so it's going to have 8 triangles. Hexagon has 6 of those triangles. Rectangle is going to have 4 of those, or sorry, a square is going to have 4 of those triangles. All right, so how am I going to use that to find the area? Well, all those triangles are exactly congruent to each other. They all have the same angles. They all have the same radii. Therefore, SSS, all those triangles are congruent. Notice they all have the same radii, and since it's a regular polygon, they all have the same base measurement. So therefore, by SSS, all those triangles are congruent. So all I need to do, since that is the area of one of those triangles, 1/2 SA, if I let n represent how many triangles they have, then all I got to do is take the area of one of those triangles, that's the 1/2 SA, multiply it by n, because that's how many triangles that would have, and that's going to give me the entire area. So I have, let's put the 1/2 first. So let's have 1/2 NSA. But think about this, right? I can make this a little bit easier, right? Think of the perimeter of the entire shape. That's just the octagon right there. Well, the perimeter would be, let's see, 8 times S since it's an octagon, but more generally, if n is the number of triangles, that's also how many sides it has as well, too. We're talking about sides of the regular octagon there. So in other words, since they're all equal to S, there's n of them. So the P for perimeter is equal to NS. And notice the formula I just wrote says 1/2 NSA. So I could substitute for NS the letter P, and we finally get to the formula. And this is the only theorem of today, which is the area of a regular polygon is equal to 1/2 PA, where P is the perimeter and A is the apothem. And that's 11/6. And that's what it says. Most people would probably in a calculator type it in PA divided by 2. All right. Take a moment, put that in your book of truth. Make sure you understand what a perimeter is and what an apothem is. If you have to rewind, play that again, do so. Okay, remember I said that this was a nice, easy formula, 1/2 PA or PA divided by 2. That looks so simple. Sure, if they give you the perimeter and the apothem, but they're not going to give you, well, they'll give you probably one of those. You have to somehow figure out the other one. So that's where the complexity enters in. So this is just a process. Make sure you pay attention. All right. It is really easy to mistake the apothem from the radius. Don't do that one. So apothem is that red dotted line. Radius is that black line right there. And notice the one we need for our formula is apothem. Okay. What is the radius good for? Well, look, it's part of that little tiny triangle right there in front of you on the screen. And well, if they only give me the radius, I can calculate the apothem using a little bit of easy trig. All right, I'll show you that. So hold on that thought. I kind of gave it away there, but hold on to that thought. All right. Before geometry, we did in geometry, I should say, we've done area of triangles, we've done area of quadrilaterals. There is no formula for anything. I gotta sneeze. Oh, bless me. For anything larger than a quadrilateral, we don't have area formulas. So remember, we worked up from triangles to quadrilaterals, but anything bigger, we get one formula, and that's only for regular polygons. All right. By the way, how would you do an irregular polygon? Well, you got to break it up into triangles or any other recognizable shape. But now we have a formula for regular polygons. As long as it's regular, there's the formula. So we have one formula for all of them, as long as they're regular. All right. These are some serious problems we're about to do. Hang on to your hats. You definitely might want to rewind and play this one again. All right. So it says calculate the area of this regular hexagon. And what did they give us? Well, they only gave us one dimension there. Well, they did tell us it's regular and it's a hexagon. There's 6 sides. And look, they gave us the apothem. The apothem is 9. So I already know one of those numbers for that formula. A is equal to 9. The problem is now I got to find the perimeter. It seems like an impossible thing, but watch this magic. All right, so I'm trying to find the perimeter. So I'm going to make one of those little tiny triangles right there, but that's not very useful if I just have one side. Can't use Pythagorean theorem. So maybe I'll put the other side of a larger triangle. Now watch this. Now here's where you pay attention. All right. Remember I said there's 360 degrees in a circle? I'm trying to calculate that angle right there, right? Remember I said there's 360 degrees in a circle? This picture right here, going from there to there is 360. So I figure out how many of those purple triangles I have for my shape. Well, my shape's also a hexagon. So there's 6 of those purple triangles. It'll be a different number of triangles depending upon what type of regular polygon it is. But in our case, we have a hexagon, so there would be 6 of those. So if I take this angle right there, if I take 360, right, divide it by those 6 triangles that I just made, 1, 2, 3, 4, 5, 6, right? Not lines, 6 lines, but 6 triangles. I divide 360 by 6, I get 60. But if I put the apothem back there, it's 60 is the entire, that thing in yellow, that's the entire. I want half of that, which would be 30 degrees. So 60 divided by 2 is 30 degrees. So that angle that the yellow arrow is pointing to is 30 degrees. Okay. Well, I know that those are equilateral triangles before. They're all regular. So therefore, it's a 30, 60, 90 triangle. And remember, we have a formula for this, right? Notice we're given the apothem is 9. So 9 is equal to a root 3, right? So to find the perimeter, right, I need to find out what that bottom measurement is right there, right? That one that the arrow's pointed to, okay? Now, since there's 2 of those tiny little triangles there, then each one is equal to a, right? And if I just double a, then I'm there. So let's see if we can figure out what a is. So we're given that the apothem is 9, and that's 9 is going to be equal to a root 3. I just solved for a. Didn't say this is going to be nice. Just process is pretty straightforward, though. So I'm going to solve for a, divide both sides by root 3. Get 9 root 3, but remember, we can't have square roots in the bottom. So we multiply top and bottom by the square root of 3. And we get 9 root 3 over the square root of 9. 3 times 3 is 9, square root of 9, which is 3. And 9 divided by 3 is 3. So a in our special right triangle is equal to 3 root 3. And that's what we need. See those double yellow arrows right there? That's what a is. So if I simply double 3 root 3, right? Then that's 3 root 3, that's 3 root 3. So double that would be 6 root 3. So one side is 6 root 3, but I need the perimeter. Well, how many sides do I have? I have 6. So I simply need to take 6 root 3. Perimeter is equal to the number of sides times the side length. The side length is 6 root 3. So 6 times 6 is 36. So I get 36 root 3, right? That's my perimeter. So I'm tossing back into my formula with 9 as the apothem, 36 root 3 as the as the perimeter. Multiply those two together, And let's see, half of 36 is 18, and 18 times 9 is 162, but I still got that square root of 3 there. And since it didn't have any units, we just put square units. Now that one is worthy of rewinding and watching that again. I will say that all of these are done similarly to what you just saw right there. We'll do a couple more. It's a lot of work, right? This previous one was one where we're given the apothem to start with. Now check this one out. Look, that's not the apothem. It's not going to the middle of one of the sides. That's going to a vertice. So therefore, that is a radius. So the ones where you have the apothem, well, this is kind of the work that's in front of you. The ones that you have a radius, well, let's see what work this involves. Okay, process is still the same, right? I still have the same formula. This time I can't throw in anything for the apothem because I know what the apothem is. So I do the same thing. I make that triangle. Well, let's see. There's the apothem in red dotted line. I got to calculate that. Remember, we figure out how many sides it has. This one has 9, so this is a nonagon. So we divide 360 by 9. What I'm trying to figure out is the angle. There's my arrow. I'm trying to figure out this angle right here, right? So that angle right there is, let's see, 360 divided by 9. There's 9 sides. That's 40, right? Therefore, cut 40 in half and we get 20. So that triangle that I'm trying to figure out is 20 with a hypotenuse of 10. That's not a special right triangle. So in other words, in order to figure out the red dotted line, I have to use some trig, some good old SOHCAHTOA. So let's see what we have here. So for my triangle, let me draw the triangle to make it a little bit easier for you to think about it. So if I draw one of those triangles, I should make it in red, but I'm not. All right, so that right there is 20 degrees. I'm drawing with a mouse, so cut me some slack. 20 degrees, and we know this side is 10. So in relationship to that angle, which angle, this angle right here, red dot, in relationship to this side is the hypotenuse. I'm trying to find the apothem, and the apothem would be the, what, adjacent side? Yeah. So that's the adjacent. This is the hypotenuse. And so what good old trig one uses adjacent hypotenuse, SOHCAHTOA? That would be cosine. Cosine uses adjacent hypotenuse. Oh, I'm sorry, Chris. Okay, don't ignore what I just said. I thought I was going to get the apothem first. This is how you would do the apothem. We do cos. I'll do that next. But I'm gonna try to find, according to my slides, I guess I should have reviewed it better. I'm gonna try to find this measurement right here. And this measurement right there is the opposite. And there's their sign, right? And so here's the basic idea. I'm trying to find this measurement right here, and then that would be the same as this, double it, and I get the entire side. All right. Sorry for the confusion. Cosine is still right for the apothem. We will do that one here. All right, let's see. So sine 20 is equal to the opposite over the hypotenuse. Looks like to solve for x, we multiply both sides by 10. So 10 sine 20 is what I type into my calculator. It's going to be a decimal number, just round. So about 3.4. Let me clear out my little drawing right here. Actually, let me just erase this part right here because I need some space right there. All right, so that's 3.4. So is the other side. So double 3.4, 6.8 is one of the sides. How many sides did we say there were? 9, I think we said. So 9 times 6.8 would be the perimeter, right? And that's when I'm getting about 61.2. That's what I'm going to type in for P. So now to find the apothem, the aforementioned cosine. By the way, could we use Pythagorean theorem now? We could, but I have done some rounding, so it would be easier to use cosine to be a bit more accurate. So I'm finding the red dotted line here. So that is the adjacent, 10 is the hypotenuse still. So same thing, 10 cosine 20, excuse me. 10 cosine 20 would be the apothem. Type that into your calculator, 9.4. There's my apothem. Where does the 9.4 go? I don't have to multiply by anything. That's just the apothem for my formula. That's just your A. Ooh, thank God for calculators. So 61.2 times 9.4 divided by 2. Round to say the nearest tenth, and you get 287.6 square units. I stated at the start of class, this is not an easy class in terms of the number of steps. The formula is pretty easy, 1/2 PA, but there's certainly some complexity there. Cool, you've done the previous one without special right triangles and used this trig here. Yep, you can. Some kids will use the trig. Some kids will use special right triangle. The only ones that are going to be special right triangles are the hexagon and then the 45, 45, 91 as well too. All right. So for homework, it's a mixture of trig, special right triangles. Remember, if you get two of the sides, you can always use Pythagorean theorem as well too. All right. Cool. Oh, that's it. Just remember we have that standard table thing. So you'll see a table and I have these letters R, A, P, and capital A. R is radius. That looks horrible. Let me do that again. R is radius, A is apothem, P is perimeter, and capital A is area. The one that caused a little bit of challenge is the one where they give you the area. So for instance, let's say the area is 10. So 10 is equal to 1/2 PA or PA divided by 2. Give me a number, make one up. Oh, thank you for picking 4. So let's say that the apothem was 4. So they gave us the A, they gave us the apothem, and we're trying to figure out the radius, and we're trying to figure out the perimeter, okay? So I can calculate the perimeter from this right here. 1/2 of 4 is 2, so I get 10 is equal to 2p. Therefore, p is equal to 5. That was easy. So the perimeter is equal to 5. To find for the radius right here, right? I believe the two shapes they give you are could be wrong, but I'm pretty sure it's a hexagon and a square. So for instance, the radius of the square right here, I'll try to draw a square real quick. That's not too bad. So we're trying to find that. We just figured out that the perimeter was crikey, 5. I should have picked the pentagon. All right, that would have been easy because then each side was be 1. So once you figure out this side right here, let's say this side right here is 6. In other words, you solve for, oh, I'm sorry. Let's say the perimeter was, I don't know, 36, right? 36 divided by 4 is 9. That would be the whole thing. So half of it would be 4.5. I'm combining two different problems here. Sorry for the confusion. And then what we're trying to find right here is the radius. So this part right here. Now, we also figured out what the apothem was. What was the apothem? I gave you the apothem was 4. So if this is 4, then we could use some good old Pythagorean theorem to find the radius. All right, hopefully that wasn't too confusing right there, but just trying to give you some directions there for how to do these. All right, so that's 1 through 12. If you run into problems, like I said, just send an email. I'll walk you through the entire problem of how it's done. So that's it for today. Keep up the hard work. You're doing a good job. I appreciate your work. Hopefully things are going well with you. And if you run into any problems, don't hesitate to ask a question. If not, I will catch you tomorrow's class.